What if I told you that a perfectly valid investment problem can have 3 different rates of return, all correct, and none of them tell you whether you should invest? That's not a trick question. It's a real limitation of the internal rate of return, or IRR, and it happens whenever cash flows change direction more than once. So how do engineers and decision makers deal with that? They use a different metric, one that always gives a single answer, uses a realistic reinvestment assumption, and leads to a clear yes or no decision. That metric is called the external rate of return, or ERR. When people talk about a rate of return, they're often referring to the IRR. IRR is the interest rate that makes an investment break even in present value terms. While it's a common metric, it can become unreliable when cash flows change direction more than once, sometimes producing multiple answers for the same project. That limitation is exactly why the external rate of return was developed. ERR shifts the focus to a more realistic assumption. Any money recovered from a project is reinvested at the minimum acceptable rate of return, or MARR. Instead of assuming the project somehow reinvests its own cash flows at an unknown internal rate, ERR treats reinvestment as external to the project. The external rate of return is the interest rate that makes the future worth of all negative cash flows equal to the future worth of all positive cash flows, when those positive cash flows are compounded at the MARR. This approach gives ERR several key advantages. It always produces a single, unambiguous solution. It avoids the multiple answer problem entirely, and it provides a clear decision rule. If the ERR is greater than or equal to the MARR, the investment is economically justified. If it's below the MARR, it isn't. Under typical engineering economy assumptions, the ERR will always fall between the IRR and the MARR. If the IRR is greater than the MARR, then the ERR will fall somewhere between them. If the IRR is less than the MARR, the ERR will again lie between the two. And if all three are equal, the decision is obvious. Conceptually, ERR answers a very practical question. What is the real return on this investment if any money I get back can only earn my required rate of return? Let's start with a simple example using a single investment. A manager is considering buying a machine for $500,000. It saves $92,500 per year in operating costs and will be worth $50,000 after 10 years. Using a 10% MARR and ERR analysis, should the investment be made? First, we separate the cash flows by sign. The initial investment of $500,000 at time 0 is a negative cash flow. The annual cost savings of $92,500 and the $50,000 salvage value are positive cash flows. Next, we compute the future worth of all positive cash flows using the MARR. The annual savings are treated as an annuity and compounded forward 10 years at 10%. The salvage value is already at the end of the project, so it's simply added to that future worth. Now comes the core idea of ERR. We set the future worth of the positive cash flows equal to the future worth of the negative cash flows and solve for the interest rate that makes those two values equal. That interest rate is the external rate of return. Solving this equation gives an ERR of about 11.79%. Because this is greater than the company's MARR of 10%, the investment is economically justified. If you want to save time, Excel can do this calculation for you using the rate function, entered as shown. When the first cash flow is negative and all subsequent cash flows are positive, we can also use Excel's MIRR function to compute the ERR by setting the reinvestment rate equal to the MARR. While we don't need it here because the cash flows are uniform after the initial investment, MIRR is especially useful when cash flows are irregular, but still all positive after time 0. Now that we've seen ERR for a straightforward investment, let's look at the kind of situation that causes problems for traditional rate of return analysis. When a cash flow series changes sign more than once, meaning money flows out, then in, then out again, the IRR equation can cross 0 multiple times. That's why IRR can produce multiple valid answers, even though only one economic decision needs to be made. For example, imagine an investment with the following cash flows. negative $4,000 today, positive $16,400 in year 1, negative $22,320 in year 2, and positive $10,080 in year 3. If you solve for IRR, you can actually get 3 different answers: 20%, 40%, and 50%. All 3 satisfy the IRR definition mathematically, but none of them clearly tells you whether the investment meets your required return. ERR fixes this by forcing all reinvestment to occur at the MARR. Assuming a MARR of 12%, we first compound all positive cash flows to the end of year 3 at 12%. We then compound the negative cash flows to the same point using the unknown ERR. Setting those future values equal and solving gives an ERR of about 12.09%. This equation isn't easy to solve by hand, so in practice, Excel's solver or goal-seek tools are the best option. Because the ERR of 12.09% is greater than the MARR of 12%, the investment is economically acceptable. Most importantly, we get a single, unambiguous answer, even though IRR produced 3 different ones. Now that we've handled the multiple root problem, let's look at how ERR helps when choosing between multiple investment alternatives. When alternatives are mutually exclusive, meaning you can only choose one, you can't just compare their individual rates of return. Instead, you have to analyze the incremental investment, the additional money required to move from the lower-cost option to the higher-cost option, along with the additional benefits that investment provides. ERR handles this cleanly. For example, suppose Design A costs $300,000 and generates $55,000 per year for 10 years, while Design B costs $450,000 and generates $80,000 per year for 10 years. The MARR is 10%. We start with the lower-cost option, Design A. Computing its ERR gives about 11.32%, which is greater than the MARR, so Design A is economically justified. Next, we analyze the incremental investment required to move from Design A to Design B. That incremental investment is $150,000 up front and an additional $25,000 per year in revenue. Computing the ERR for this incremental cash flow gives about 10.26%. Because this is still greater than the MARR, upgrading to Design B is justified. At that point, Design B is selected. In summary, the external rate of return equates the future worth of negative cash flows with the future worth of positive cash flows reinvested at the MARR. It avoids the multiple answer problem of IRR and provides a clear decision rule for single investments, incremental comparisons, and irregular cash flows. ERR is a powerful and practical tool for engineers, managers, and investors who want to make sound economic decisions without getting lost in confusing math. If you found this breakdown helpful, consider subscribing for more engineering economy explanations. Thanks for watching, and I'll see you in the next video.